Last time we talked about maximum flow, the application of it, and we didn't finish it. So let me try to finish it today. So let me recap, right? We look at the problem called circulation, and in this problem, what you have is that you have a directed graph, and then you have edge capacity, and then there is a vertex demand, right? Not just S and T. Every node can have some demand. And what you want to find is to assign flow into edges so that the inflow minus outflow of a node V would be equal to the demand at V. You want to do this. Otherwise, decided is impossible. And we saw how to do this, right? How to do that? Well, just kind of connect the source to every node with negative demand and the sink to every node with positive demand, right? And then you check whether max flow value equals to the sum of the positive demand, which will be the same as the sum of negative demand, actually. And because you know that actually if this is not the case, then it cannot have, like, you just cannot have, like the circulation cannot just exist. Yeah. The sum of negative demand and positive demand must be the same. Otherwise, the circulation doesn't exist. Okay, that's from the last time. Okay, now let's do something even more. What if the circulation here, we have more constraint, that is we have a lower bound. So the setting is this. Here, now each edge, you have a tuple L of the edge and C of the edge. So L here means the lower bound, C means the same thing, capacity. What you want to find is to find circulation F such that the flow on an edge is at least L of the, is at least the lower bound and is at most the capacity. Okay, so now we have the lower bound. And now let's say that the demand on each node is 0. The demand on every node is just 0. Okay. So what we want to see is, now I just want to know if there is a way to assign flow such that this is true for every edge. Okay, that sounds more complicated, but actually we can do it. How to do it? Well, the strategy is to convert the lower bounds to demand. Okay. So imagine that you have this edge, right? And it says that you need to flow one flow here through this edge. Now, suppose I can, suppose that somehow I know that this node will have flow, suppose that I just try to, okay, maybe I just show this. What I do here is that I want this node to send at least one flow for sure, and this node to receive, what I mean is that if I want that, okay, let's see. The idea is actually quite simple. Before go to notation, the idea is just that I want to say that this node will need to send flow, one flow for sure, and this node will need to receive one flow for sure. Okay, and if that is the case, then like no matter what, the flow must go through this edge. Okay. Maybe good. So maybe I can just do one way to do is just to do this thing. That is, maybe I just can add one node here and one node here. Okay. And I say that this guy must receive one flow, and this guy must send one flow. And then you know just from here that like some flow must come here and some flow must go here. And now if you can satisfy this demand on this node, all you need to do is just like now just send flow between this guy and it will be the flow between this on this edge. Okay. That's it? Okay. But okay, what I'm gonna do actually is just some similar to this idea, except that I don't even introduce any new nodes. Okay. So what I do is just set the capacity, set the demand of this guy to be -1, set the demand of this guy to be 1. Okay. And then, okay. So what does it mean here? It means that at the suppose that I can find a flow such that this guy receive net flow of 1. This guy will be able to send flow out of it by 1. If I can satisfy this demand, and now this is now reduced to 0, not that. If I can satisfy this demand where this is now 0, I will be able to satisfy this demand, this lower bound, just because this guy have one unit of flow on it. This guy will have -1 unit of flow on it. So I can just now send the flow along this edge so that it satisfies this guy. It satisfies the edge above here. Okay. Make sense? Okay. So, and I also need to reduce the capacity by 1 because I cannot preserve one capacity for 1 unit of capacity to send through this one later after I satisfy this demand. I just, yeah. I hope that's understandable. Okay. And basically just do this on every edge. For every edge with lower bound, you can just put some for every edge with the lower bound on one end you increase the demand, on another end you decrease the demand, and you reduce the capacity. If you can satisfy a flow with after you do this operation, you will be able to satisfy the flow with the lower bound. So once you do all of this on every edge, right, what you get is just start from some graph with lower bound, you just get a graph with only capacity and demand on each node. And now you're done because this is just now a circulation problem with demand on nodes and capacity. So all you need to do is just reduce to max flow using the same reduction. And just check if max flow value is the same as positive demand, sum of positive demands. Yeah.
Why is it always necessary that the lower bounds coming in is equal to the lower bounds going out?
Oh, you mean what do you mean the low bound is on an edge, right? So
Yeah, so I guess like why is it necessary that for each node the lower bounds of edges coming in is the same as the lower bounds of edges going out?
wait, the lower bound here is just on an edge. What I do is just convert this lower bound to demand on two nodes here. And what you ask, why do I set this to why do I increase and decrease the demand on both endpoint with the same amount? Is that your
I'm
question?
just wondering like how it works with like multiple edges coming into a node when there's like multiple lower bounds. Because it like say you have the middle node there, then there's like several edges connected to it. So do you modify the demand based on each of those edges lower bounds differently?
Yeah, if there is an edge with this lower bound, right? I increase the capacity, increase the demand here. For this edge with, let's say, lower bound 3, I would decrease the lower bound, decrease the demand here.
Okay.
Yeah. So for every edge, you just look at both of its endpoint and increase and decrease lower bound according to the low.
Okay.
Increase and decrease demand according to the lower bound on each edge.
Okay.
Yeah. Okay. So in this particular case, the answer is that there is no circulation because you can find some cut that certify that the flow is too small. But that's not the point. The point is that you have reduction. Okay. So let's see some more kind of more practical, I guess, problem. One example is this. Suppose that there are matches between teams, and what you want to ask is that whether one particular team have a chance of winning the tournament. So in this diagram, this is just the number of wins so far for each team. Minnesota win this much, Detroit have won this much, and Chicago this much, and Cleveland just this much. So Cleveland so far is like the bottom of the rank, have like worst rank. And now then there are some this diagram says that this is the number of remaining match between each team. Okay, so Cleveland and Detroit still need to play for another 4 matches, and so on. Okay, so now I ask, with these remaining matches, is it the case that Cleveland can still be the first of the tournament? So that's the question. And so if you ask this, the first thing you should how do we decide this, right? The first thing we can say is that, okay, let's assume that Cleveland just win every remaining match that it will participate first. Let's assume that, because otherwise we just ask if there is any chance at all, right? So just assume that Cleveland won everything. If that is the case, then the number of wins that Cleveland have is going to be 41. But this means what? In order for Cleveland to be the first guy in the tournament, then Minnesota can win at most 1 more, and Detroit at most 3 more, and Chicago at most 4 more. Okay. And now you can think like this. This diagram now looks kind of similar to a circulation problem. how it's like each of these remaining mesh, you think of it as this is like the number of this number 6 here is like the number of wins remaining that need to be distributed somehow to Chicago or Minnesota. So the number of wins here is something looks like the amount unit of flow that need to be distributed to some team. Okay, so the like these matches looks like the source of the number of wins, and each of this team here, like this is like the sink capacity. Like this guy cannot receive more than 3 wins. This guy cannot receive more than 1 wins, and so on. Right? So we kind of ask, this is like the source of wins. It needs to be distributed to this guy, and this guy can receive like this number is like the sink capacity for each team. And if there is a way to distribute these wins so that it respects the sink capacity, then Cleveland can be the number 1 in the tournament. So I hope that makes sense intuitively. Let's see the formal reduction. Okay. So So you see, because each of the remaining mesh look like the source of wins. So what I do is I just connect the super source to all of this guy, to all of the remaining mesh. Okay, this is like pair of teams. This is each of the remaining meshes. Okay, and then there is a team, 3 teams remaining. This guy connect to sink, and the capacity of this would be like the number of maximum allowable win for each team. So this is like a sink capacity on each of this guy. Okay. What about this number? This should be the number of wins that these mesh need to distribute somehow. And where can it distribute to? Each of this guy, it will just distribute to either Minnesota or Chicago. So this guy will connect to the 2 team that this mesh the 2 teams that participated in this mesh. And you just you can put the capacity of 6 here, or actually, yeah, you can put the capacity of 6. That's fine. Okay. So that's a reduction. And now, can you tell me so this graph is clear, right? How do we construct it? Can you now tell me what is the condition that we should check whether Cleveland can win or not from this graph? Like suppose we solve max flow on this graph, then what should we check?
You want it to be greater than or equal to the number of wins to be distributed.
So yeah, which is what number in this case?
8.
Yeah, exactly. So basically, you just if Cleveland have a chance, then max flow should be 8. Okay. That is basically you can distribute all the number of wins to all of this guy, right? So that each of this guy don't receive more than the sink capacity. Like if the max flow is really 8, then all the wins can be successfully distributed, and you respect the sink capacity. But yeah, in this case, you see that there is a cut of size 7. So yeah, in this case, like Cleveland have no chance. But yeah. Okay, so that's just another example. But I think the point that we made in this class is that you see that it's just like a large list of applications for MaxFlow. I just give you a few things, but there are just much more than that. And to wrap up, so you see that many algorithmic problems just reduce to MaxFlow. And not just algorithmic problem, many theorem, like which is purely structural, like purely combinatorics, like Menger theorem, we saw this, Hall theorem, that just reduced to mean cut MaxFlow theorem. So you see that like it's a powerful thing to know, not just as a black box for solving some algorithm problem, but for proving math theorem which have nothing to do with algorithms. And now what we're gonna do is just to look at another step, which is linear program. It has the same flavor like MaxFlow, but it's much more general. And like tons of algorithmic problem reduced to LP, to linear program, and tons of theorem reduced to LP duality. We will learn all of this next. It has a, yeah, okay. It's like linear program is like a strict generalization of MaxFlow. Okay. So that's the next thing we're gonna look at. But before that, I want to tell you a bit about maximum matching. So we saw in previous class that to solve maximum matching, you can just solve it using one MaxFlow call, right? But one MaxFlow takes, at least what we learned in class, it takes mn squared. That's Dini's algorithm. Or mn if you run Ford Fulkerson in the unit capacity graph. But what we're gonna learn today is how to solve maximum matching using root n blocking flow. So the time, instead of mn, you will get something like m root n. And this is simple enough to teach in class. So it's quite nice. Like, I mean, if you solve it using MaxFlow, there is like a new MaxFlow algorithm that run in linear time already, but that's just too complicated. I want to tell you how to solve maximum matching in m root n time. Okay. So I just need to recall something about Dini's algorithm. So if you recall Dini's algorithm, right? In each iteration of Dini's algorithm, we just augment the blocking flow in G prime. The graph, like, is a subgraph where you, like, when you look at the residual graph, and when you layer nodes according to its distance from the source, G prime is just contains all the edges in the forward direction, and you augment blocking flow in G prime. Doesn't matter too much, but the point is that after the iteration in Dini's algorithm, you have that the distance from S to T must be at least D, because in each iteration the distance increased by at least 1. I just need you to recall this thing. But if you run Dini's algorithm, we know that after n iteration, the total time is mn squared, because each blocking flow takes mn, and there are n iterations. Okay, so keep this in mind. This is just to refresh your memory. And now let's look again at maximum matching problem, right? You have a graph, bipartite graph, A and B, A on the left side, B on the right side. What you want to find is to find largest maximum matching, the largest matching. And so one reduction to solve like last time I told you how to solve maximum matching by just create flow problem and then set the capacity of each node to be 1. If you recall, last time the capacity is on every node. But you can as well just set the capacity of each edge to be 1 as well. Doesn't really change. Like if you solve max flow in this graph where the edge capacity is 1, the max flow will correspond to maximum matching. Okay. But instead of calling max flow as a black box, which can be slow, we will try to do something not black box here. Okay. So let's look at this graph, and one observation, the initial observation is this. If you have this graph, and if you look at the flow, integral flow, right? And then suppose f is just some integral flow. And now I claim that the out degree of any node on the B side will be 1. Okay. Always. Okay. Why is that? So initially, before you have any flow, the out degree is 1, just from this picture. But why is it the case that for any residual graph, the out degree of B must be 1? So you have B, you have some in degree, and right now there is just some out degree, 1 out degree. Anyone see why is it the case that if you look at the residual graph, out degree must be 1 as well?
If it was more than 1, that means 2 edges had to, with flow 1, had to reach BJ, and it only has 1 outgoing edge in the actual graph, and it has to go to the sink, so the conservation would be broken.
Exactly. So you know that the capacity of this guy is 1. So if there is some flow that goes through BJ, there is only 1, like the flow can come from only 1 node and go through BJ. Okay. There cannot just be more than 1 ingoing flow. But if that is the case, then what you get, in the residual graph, this edge would be flipped, and this edge would be flipped, and outgoing edge would be 1 again. Out degree would be 1 again. Okay. So you just know that like the flow going through it is just one flow. So once you flip the edges, then the out degree is 1. Okay. So keep this in mind. And now, imagine this. What I'm going to do is just run Dinitz's algorithm in this graph. Okay. But instead of running Dinitz's algorithm for n iteration, let's say that we stop early. We just stop the Dinitz's algorithm as a root n iteration. Okay. So after root n iteration, we know that the distance from S to T is at least root n, or to root n. And what you get is that you can layer the graph like this, right? So let's say that we layer vertices according to the distance from S. And because we layer the vertices according to the distance, you know that all forward edges cannot skip layer. Otherwise, it's not going to be layer, it's not going to be, if there is, let's say, this edge from here to here, then the distance from this guy would be smaller, right? So you cannot have forward, all the forward edges cannot skip layer. Okay. And now you also know that the layer must alternate between a set from A and B, because you know that edges only connect between the A and B. There is no edges between A and A. There is no edges between B and B. So if there is an edge here, that it must be one endpoint must be from A, one endpoint must be from B. So you get this alternating layer between subset of A and subset of B's. And another thing is that you see that Bj always have out degree 1. So the number of edges that go out of this guy is just the same as the number of nodes of B in this layer. Okay. So this is just some structure of this graph. But now, once you see this structure, now I claim that actually there must exist some cut in some ST cut in residual graph of size just root n. Why is that? Because you see, first, there are root n many layers here, but there are just n nodes. So first thing is that I claim there must exist a layer of Bi of size something like root n, right? The number of Bi is actually just n over t. So yeah, actually this is true. Yeah. So the number of nodes in Bi is just, maybe I just do this, t over 2. Yeah. Let me just do this thing. Yeah. The number of nodes in B in total is just n, but there are root n many layers of B's. B is now partitioned into root n many sets. So some of the subset of B's must have size just root n. Make sense? The first thing you need to know is just that exists some Bi of size root n. Okay? Yeah. I partition B into a K set. One of them must have size just at most K, 1 over K fraction of the set. But here, I partition it into root n set. Some of them must have size at most root n. Nothing here. But let's say that this guy, suppose that this guy is a guy that with, this guy is the one such that the size is at most root n. But I know that the out degree of each of this guy is just 1. So the number of edges crossing this cut in the forward direction is just the size of B2, which is root n. And you don't need to count, we don't count edges that go backward, right? We only count edges that go forward. And also the edges that go forward cannot skip layer. So I really can just count the number of edges between this guy. Okay. So question up to this point, that there is a cut of size root n in the residual graph. But if there is a cut of size root n in residual graph, then it means what? It means that after another root n rounds, S and T will not be reached, like S cannot reach T. Because in each iteration, you will basically increase the value of the flow by at least 1. But there is a cut of size root n up to this point. So you can increase the flow by at most root n many rounds from now. So it means that after 2 root n iteration, we just conclude that you cannot continue by another root n iteration. So after 3 root n iteration in total, you're done. You don't need to continue for, like, no matter what, just actually do the same algorithm like Greenwich's algorithm. But we know that it must stop after root n iterations. You don't need n iterations. So which means that the total time is going to be m root n because you need root n blocking flow. But blocking flow, as you will show in your homework, is just linear time when the graph have unit capacity. So that's how you get m root n. And yeah, this algorithm has been like the best algorithm for like almost at least 40 years until it is recently improved 5 years ago. And now the state of the art now is linear time. But this is like a simple algorithm that just works and has been the state of the art for a long time. Okay, question about this? Okay, so what I want to tell you next is linear program. Okay. So what I want to tell you today is just what is linear program and what is LP duality. What is that thing? It's mainly about learning language in this class, and there's nothing about algorithm today. But it's going to be important because from now I will use the language related to LP throughout the class. Okay. So let's look at one simple example of LP problem. Imagine that you are a baker and you want to decide whether to bake a cake or a cookie. Okay. And so the situation is that for a cake, you can sell it for $3 per unit. And for a cookie, you can sell it for $2 per unit. Okay. And so the situation is that, I mean, at the end, you want to maximize your money, but you need to respect your budget. Okay. So suppose that you have some budget which says that, okay, you have 2 units of flour and 6 units of sugar. And to make 1 unit of cake, you need 2 units of flour and 3 units of sugar. And for cookie, it requires 1 unit of flour and 4 units of sugar. Okay. And the situation is like, so if you want to maximize money, but still respect the budget, cannot use more than this resource. Like you have this limited resource. So the question is how many units of cake and cookie that you should produce. Okay. And this question can be formalized as a mathematical problem. How? Well, you can say that let x1 and x2 to denote how much you make cake and cookies. Then what you want to maximize then is just 3x1 plus 2x2. Right? This is just the total amount of money you get from making a cake or cookie. But you have a constraint on your resource. So if you make, like, you have total 2 units of flour, and for each of 1 unit of cake, you need to pay, like use 2 units of flour, and for each unit of cookie, you need 1 unit of flour. So that's why you can write it as this linear constraint. You also have the similar constraint for sugar. And also, you can only produce non-negative unit of cake and cookies. So you need to put this constraint as well. Yeah. Although it's not in the English, but you need to put it in math. Okay. So this makes sense, right? Just how to formulate some problem into this mathematical formulation. So let's try to think of this problem now in a geometric way. So what you have is that, let's say that I plot the graph where this is x1 and x2, right? And well, there is like the constraint for flour. You can look at it like this. It's just some linear constraint, and say that like you can only produce cake and cookies. Like if you look at any point in this thing, it says like how many cake and cookie that you produce, and this line says that you can only produce things in this area. Okay. In this area. Another constraint for sugar would be like just another line, right? Like some maybe. This is a constraint for flour, and another constraint for sugar. It looks like this. Okay. And with these two constraints, it just defines some feasible region of, like this purple region is just any, like the point where you can produce your cake and cookie with respect to your budget. But so as long as you are in the purple region, you have enough budget. But now what you also want is to maximize the objective, right? And to maximize the objective, you can think of it as, this is the amount of money. This looks like just, this objective is just some direction. So it basically says that you want to go as far as possible in this direction, within this region, right? And now you can see that actually this point is the point that goes furthest in the direction of objective. How to see that? Well, you can just project this point to the objective function, and it's here. And if you take any other point in the feasible region, let's say this point or other point, once you project it to the objective direction, it will go like a less further, like it doesn't go as far as this point. Yeah. So you get that this point in the feasible region is the best solution. Okay. Make sense? Okay. I mean, actually, it's quite easy to see also that once you have a feasible region and you have some direction, you actually know that your optimal solution must be at the corner. Even if I don't know the objective, where is the direction of objective, the optimal point must be at the corner, because if it is inside, like in the interior of your objective, right, in the interior of this visible region, no matter what direction it is, you can always go further. So you actually know that the optimal point must be the corner. And now, once I fix the objective, that now depends on the direction of objective, which corner is the best one. So to check which corner is the best one, you can just project into the direction of the objective and see which one go the furthest. Okay. So basically, in this case, yeah, this point is the best, and you get $3.6 by making this much cake and this much cookies. But in general, right? What linear program is just this kind of problem, where you have n variables. Think of variables as the kind of products that you can produce. And m constraint is an m kind of resource that you have as a budget. And then the linear program is the problem of this form, where you have linear, you want to maximize this linear form with respect to linear constraints. Okay. So everything needs to be linear. You cannot have degree 2, all the xi will have degree 1 in this thing. Yeah. So both objective and constraint are linear. If you have that, that's linear program. And this thing can be succinctly represented here, like this, right? Just put all the A's here, collect all the A's into a matrix. Matrix of size m by n. And then you have all the B's here. You put it into vectors. And now the constraint can be written as ax at most b. For C, you just make a vector for C of C, and Cx is just now the objective. Okay. So that's the this is called standard form of linear program. Okay. Okay. So now let me tell you that this standard form of linear program is actually very expressive. Why is that? Well, let's see. So suppose that you have n variables and you want to maximize this thing subject to this linear constraint, right? And you have that each variable need to be at least non-negative. So what if instead of maximizing this function, what if I want to minimize? If I want to minimize a function, how can I convert the problem into standard form?
Like negative C.
Yeah, exactly. Just if you want to minimize this, it's the same thing as maximizing the negative of what you want to minimize. Okay, so I can, instead of having minimized things, I can just say, okay, just make it maximize again, but put negation to the whole function. So that will work. What if this, instead of having at most constraint, I want to have at least constraints? How can I convert this into standard form?
Wait, take the negative of that, row.
Yeah, exactly. So we can do the same trick. Put the negative of everything. Just multiply the whole inequality by minus 1. You get at most. So note again that like every coordinate, every entry here need not be negative number, right? Like all the aij can be negative or positive. This is fine. I mean the coefficient can be negative or non-negative or positive. So what if we want to have equality? How can we get this, like convert this into standard form?
You have both positive and negative, so that's less than equal to and greater than equal to, so it's equal.
Yeah, exactly. So you can just put like at least and at most, and then make the at least one to be at most again, and put it into the standard form. Okay. So that's just by putting these two constraints and make it into the standard form at the end, you get a standard form linear program. What about this one? So normally I have that everything here is at least 0. Now what if I want to drop one constraint, that drop this xi at least 0? I'm okay with having xi to be negative. But every other variables is still not negative. So to drop this thing, how can I convert it into standard form again?
I'm not sure if this will work, but you could flip the coefficients of every single coefficient of xi. So you can create like a second linear program that has xi necessarily like equivalent to negative, and then you can solve both and take the maximum, so it can be positive or negative.
Yeah, so that will work. Just basically solve one linear program where like where you say that x1 is positive, and then another linear program where you kind of negate all the coefficient of x1. That will work, but what I want to do is to just have one linear program. But yeah, the trick is this actually. Just create, kind of combine like what you said into one linear program. So create x1 prime and x1 double prime, and replace each of the appearance of x1 by this thing. Okay. Then if your solution need to be such that x1 is negative, what you will do is just you set x1 double prime to be positive, and it will work like x1 when x1 is negative. Okay. So yeah, so that's how to go, and so you see that this standard form of linear program is already very expressive. It is very flexible whether you want to have maximize, minimization, equality, inequality in both directions. All of this you can always convert it into a standard form linear program. Okay, so you see that it is really expressive and can be used to solve many things. And a lot of problem can be modeled into linear program, and like optimization problem in manufacturing. This is a linear program problem, and also MacFlow. Let's see how to model MacFlow using linear program. Well, it is almost from the definition of MacFlow. Like you have linear inequality here, which says that the flow on every edge need to respect the capacity. You have this thing which is a linear constraint here, right? we say that the flow must be conserved on every node except S and T, and you want to maximize this linear form, which is a flow going out of S. So yeah, max flow can be modeled as a linear program, and it turns out that linear program can be solved in polynomial time. So that's another way to solve max flow in polynomial time, just solve linear program. So this is a big deal, because the problem that is as generic as this turns out that you can solve it in polynomial time. The first, I will not teach you how to solve it actually, because that takes another class, like another course, the whole course. The first algorithm is called simplex. This is from like more than 60 years ago. It's still used until now, actually. Very fast in practice, but in worst case, it takes exponential time. And then like some time after that, there is a general method called ellipsoid, and that is fast in theory, but not so fast in practice. And now another class of algorithm called intermediate point method. This is quite fast in practice and theory. In any case, in this class, I'm just going to assume that given linear program, you can solve it, okay? And see how to use this. And okay. So let me try to tell you a bit more about some geometric terminology related to linear program. Okay. So you have this linear program, right? And similar to what we have seen, which is two-dimensional geometric interpretation of what is going on. In general, you can have geometric interpretation of any linear program, but it's going to be more than 2 dimensions. Okay. So if X here is like a solution of size n, like now the picture that you should have in mind is some n-dimensional picture, but we're just going to draw something in 2D because that's how physics work, I guess. So what you have, right? Like, just look at the jth row of the matrix A. The jth row looks like the one constraint that you have, and so the jth constraint A j times x at most b here. This will be one constraint, which says that like you only care about anything on one side of this hyperplane. Like when you look at jx equals b, this is like a hyperplane, right? It's like not just a line, but some hyperplane that separate a space into 2 sides, right? And this thing says that you only look at one side of the plane. And then you have a bunch of constraints. Okay? Each of the constraints says that you look at one side of the plane. And then in the intersection of all these constraints is going to be your feasible region. Okay? This is now high-dimensional thing, but yeah, it's just like similar to what we have seen before. And the intersection of this half space here it has a name. It's called polyhedron. So and now this polyhedron can be bounded or unbounded. So if I have this one, then it would be bounded. So the volume of this area is finite. If I don't have this thing, then it's unbounded. Like you actually, the volume of this area is like infinite. Okay. And so given a bunch of constraints, you basically get a feasible region, which is the polyhedron. And then once now you fix the objective function. The objective function is like some direction, right? It can point to any direction. Let's say it just points in this direction, just downward. Then once you fix the objective function, it will fix the optimal point. In this case, it's just the one that is go furthest in this objective direction, which is this guy. Okay. And you can have like some physical interpretation of LP as well. Like you can think like the objective function as the direction of gravity. And then like let's say that you drop a ball inside some physical region, and then the ball will basically keep going until it stops. Where it stops is going to be the optimal point. Okay. So let me ask you, can there be more than one optimal solution? So yeah, basically there can be more than one. In this case, there is just one. But what if I have some constraint like this? That is just like this is just like a kind of orthogonal to the direction of objective, right? If I have the constraint like this, like then any guys in this plane, in this segment will be optimal. Okay. So just a bunch of terminology, but I think it's quite intuitive, right? Okay.
Yeah, this is like a notational question, but say that the objective function is in the direction of it being unbounded. So do you say that there's no optimal solution, or do you say that there's infinite number of optimal solutions?
There is no optimal solution in that case. Yeah. So yeah, good question. That's the next thing I wanna say. That is, given any linear program, then there are three possible outcomes. The first case is when optimal solution exists. Another case is when it's unbounded. That is, if the polyhedron is unbounded, and let's say that your objective going in this direction, then you can go infinitely. That's when we say that it's unbounded. Otherwise, another case is when this polyhedron is just empty. Like it's just the intersection of everything. Let's say I have another constraint says that anything below this thing, then the intersection now is empty. So there's nothing to optimize for. In this case, it's called infeasible. The problem is infeasible. Okay, so now what I want to do next is to motivate you to the concept of duality. This is like very important concept in CS or in mathematics even. So let's say that you have optimal, like let's say that from now I did use op to denote the maximum value of this program, of this LP, the best objective you can get. Okay. Now suppose that I want to lower bound opt. There is a simple certificate that gives a lower bound of opt. How? All I need to do is just suppose someone give me some feasible point for this program that it respect all the constraints, and if this point have objective at least 10, has objective let's say 10 exactly, then you know that opt must be at least 10. So there is a simple certificate of the lower bound of opt. So any feasible point in the program is a certificate for the lower bound of opt. If now I ask similar thing, is there a way to show some simple certificate that gives the upper bound of opt? How to get that? And that is not clear, but this is what LP duality is for. Okay. So the picture that you have in mind is like something like this. If this is your opt, to get a lower bound, there is easy way to get a certificate for that lower bound opt. But not clear right now how to get certificate that upper bound opt. So now there is a simple way to get a certificate that upper bound opt. So let's see some simple example. Okay. So we have seen this linear program before, the linear program in the beginning. And now imagine this. Imagine that I kind of introduce two variables. For each constraint, I introduce one variable y. Okay. And now, imagine that I kind of multiply y to the constraint on both sides. Okay. And suppose that I set y1 to be 2. Then you can check one thing, that is, okay, if I multiply y1, 2 to this thing, right, I get that this thing multiplied by 2. Now, important thing is that this thing is at least the objective. You have the objective here. This objective is dominated once you multiply the first constraint by 2. And then this thing is at most 2. So you get that this whole thing is at most 2 by 2, which is 4. So you can kind of say that, okay, this looks like the objective here is bounded by 4 now. So let me try to be formal. Okay, like I claim that just once you have here, I can assume I can conclude that opt is always at most 4. So you see. Like the first inequality here must be true, right? Because you can just check that this is 4x1 plus 2x2. And because all the xi are non-negative, so this is at most this one. And now you also know that as long as x are feasible, it must respect this constraint. If your point x is feasible, it must respect the constraint. So you know that this thing is at most 2. So the second inequality holds for any feasible point x. So now you get that what you get is basically now this is objective. You get that this objective is at most 4. And this is going to be true. You get the upper bound of the objective as long as x is a feasible point. So you get that, right? Now I just gave the upper bound of the objective as long as x is a feasible point. So it means that opt is at most 4. So what if I do something similar? Like I don't need to just set y1 only. What if I try to find a combination of linear? Like I try to find like some linear combination of the constraint so that it dominates the objective. So let's say that I now set y1 to be this, y2 to be this thing. Multiply the first constraint by y1, the second constraint by y2. And I can check that this thing, this sum, is at least this objective. Now, if x are feasible, this is going to be at most 2 from the constraint above. This is at most 6. This gives another upper bound of the objective, which is better. Now it's 3.6. Okay. And know that like you know before that there is some point such that op is at least 3.6. So you get like a tight lower bound and upper bound here. And this is not coincidence. But before we go there, so you see that there is a way to give an upper bound of opt. That is, as long as you can find linear combination of constraints that dominate the objective, that will give you upper bound. Okay. So, makes sense up to this point? So now the punchline is this. The problem of finding the best Y, the best linear combination, itself is an LP problem. Okay, so that's cool. So let's see. So let me try to say why like the problem of finding this Y is an LP. So you see, you have this LP, right? And now what we want is to find the linear combination of constraints that gives smallest upper bound of the objective. So it means what? In this case, I want to, like, in this problem, right, we want to try to find y1 and y2 such that once I multiply y1 and y2 here to the constraint, right, I get the best upper bound. So I want to minimize this thing, y1 times 2 and y2 times 6. I want to minimize this thing. As I want to minimize this thing, as long as this linear combination of a constraint dominate the objective. Okay. So you agree? Like this is our problem. And now let's rearrange it a bit. Instead of putting y here, let me factor it, put x here instead. Like rearrange things a bit. And it will, and now it implies that this thing needs to be at least 3. This thing needs to be at least 2. And now I can eliminate all the x, and I get this one. So this is now just linear program on y. Okay. And this is called the dual LP of this original LP. Okay. So in general, given any LP in the standard form, once you write the dual, you get this thing. Very succinct representation of the dual. And in our example, it's basically this thing, these two things. And now, what is cool is that if P, let's say P is some LP, if you take the dual of P, and take the dual of that dual, it's going to be your original problem, P. Because you can just check syntactically here that when you have this guy, convert to this guy, and if you just flip things so that this is at most and this is maximization, and take the dual again, you get back this guy. So dual of dual is primal. That's why it's called dual. Yeah, it's just the flip side of your problem. although one very important point I want to make is that although this is like dual problem, primal and dual solution actually live in the totally different space, right? Here, x and y in this simple example, they live in like a R2, but in general, if the matrix here is not square matrix, if it's a rectangular matrix of size m by n, then x live in n-dimensional space, but y would live in m-dimensional space. So, okay. So in general, primal constraint correspond to dual variables. Primal variables correspond to dual constraints. And if the LP is not in the standard form, if the LP is not in the standard form, you will basically can get this kind of things. So what I show you is just when you have only this constraint and all the x is at least 0. So that's why you get all the y at least 0 and the constraint of the dual is at least. But if it is not standard form, you can check that the correspondence looks like this. Okay, so I am out of time. So next time, what we're gonna do is we're gonna show the relationship between these two programs, a primal and dual. This is actually a tight relationship. And let me spoil you, actually. They are always the same. The objective, this is like a primal is a maximization problem, dual is minimization problem, but they will meet at the same point. So yeah, for that we do next time.